Hello and welcome to another video of magnetic fields. Today we're going to look at the magnetic force on a current carrying conductor. The outcomes for today are looking at magnets, magnetic materials, moving charges and current carrying conductors, talking about them experience of force in a magnetic field. We'll also talk about the direction of the force on this conductor or an individually charged particle moving at some angle to a magnetic field. We'll determine the direction of the force, the magnetic field, the charge movement if we're given the direction of the other two, and we'll solve problems involving the formula of F equals ILB sine theta for a current carrying conductor. So magnetic interactions is the first thing we're going to look at. Magnets, magnetic material, and moving charges, as well as current carrying conductors, experience a force in a magnetic field. The picture below shows an example of this if we would use a bar magnet, and this is within a uniform magnetic field. In a previous video we talked about the fact that the north pole of a magnet experiences a force parallel to the magnetic field. The magnetic field is given as the direction that the north pole of a compass points. So if this north pole of the magnet is experiencing the force parallel to the magnetic field, while the south pole experiences a force that is anti-parallel to the field. So now we've got this parallel and anti-parallel again. Remember that parallel is moving with the field and anti-parallel is moving against the field lines. In this example here, we can see the uniform magnetic field between two bar magnets and the magnetic field surrounding the current carrying conductor. So here we've got our current carrying conductor. Using the right-hand rule, you could probably figure out which way that is going. They haven't used the notation, but given that the magnetic field is going anti-clockwise, you would assume that the current is coming out of the page. So using that thumb pointing towards you, looking at the screen, your fingers would curl in the right direction. And here we've got just two bar magnets, a north and a south, and it's traveling from north to south. When the current flows through a wire, a magnetic field is set up around it. Magnetic field lines cannot cross, so therefore if they're pushed near each other, they are distorted. The net result of this distortion is to create a force on the current carrying conducting wire. The picture on the right shows an example of this with individual magnetic fields interacting and the resultant force, which is F, on the straight current carrying conductor. So here we've got this current carrying conductor that's generating its own magnetic field, and it's within an existing what was uniform magnetic field. So we've combined the two images from here and we've put them together. Given that the lines can't cross, they can't just run over the top of each other, they're sort of pushed out of the way to make space for this magnetic field. And as a result of pushing all these down, it ends up with this kind of push force, this magnetic force there, that's pushing this particle in that direction. If we were to reverse the field, the force would be reversed, so all of these directions would change, and if the current was also reversed, then the force would be reversed. An important sentence from this concept is that a current carrying conductor placed in a magnetic field experiences a force. That is the fundamental concept that everything we're talking about in this lesson is based upon. It's based on that image from before, talking about the fact that these magnetic fields will interact, they won't cross, and therefore as a result you'll have a force pushing on it. A current element is the product of the current and the length of a small current carrying conductor, i.e. I times L. This is what we refer to as the current element. The magnitude of the magnetic field is defined as the force per unit current element placed at right angles to the magnetic field. So we can write this as the magnetic field is the force per current element, but force is just our vector F, and the current element is the IL. So here we have F over IL is equal to magnetic field. Previously we defined the unit of the magnetic field as the Tesla, but from this we could also see that this could be newtons per amp meters. So we have two different notations. Tesla is the SI unit, but we could also refer to it using these SI unit combinations of newton per amp per meter. The interaction between current, magnetic field and the force can be identified using the right-hand rule again. In this version, which is a little bit different, the thumb is the direction of the current, the index finger is the magnetic field, and the palm or the middle finger is in the direction of the resulting force. So now we get this three-dimensional right-hand rule. Some people just use the palm, and you've got your thumb in the direction of the current, which it always is, finger or fingers in the direction of the magnetic field, and then the palm points in the direction of the force, or you can use the 3-finger version, either way. So this is an expansion. The right-hand rule that we talked about earlier is often called the right-hand curl rule. So direction of the current, fingers curl around in the magnetic field direction. In this one, we've got the 3 to signify current, magnetic field, and force. As a side note, for anyone that has seen cross vectors, which are sort of similar but different in concept to a dot product, you may notice that the force is always the cross of the current and the magnetic field. So mathematically, when we look at this, they write it as M cross C equals F. Magnetic field cross the current gives you F. Mathematically, this is how you generate a field or a plane that's perpendicular to the 2 other vectors. So this is actually treated as a cross product at a higher level. When you go to university physics, they refer to this right-hand rule for electromagnetism using cross products. But we don't need to worry about it for this. We just stick with the basic concepts. You can use the right-hand rule, and you're not expected to know this level of mathematics. Looking at this picture again from the previous slide, you can see that as the fields cannot cross, they interact with each other. This is like stretching apart a net or a slingshot. So because the field wants to return to its normal state, that's why we've got this upward force. This occurs when the current is perpendicular to the surface. If the current traveled in the same direction as the magnetic field lines, the magnetic field of the wire here would be perpendicular to the other magnetic fields and wouldn't have an interaction. So they need to be running on the same plane. So for this, ideally, we have this running in a perpendicular scenario, and we get a force generated here. So key concepts here are that if the current is parallel or anti-parallel to the magnetic field, the force on the wire is 0. We would describe this as an angle theta equals 0 to the field. If the current is perpendicular to the magnetic field, the force on the wire is maximum. We would describe this as an angle of theta equals 90 degrees to the field. So what about if we're just at some random angle theta? We know the 2 extremes. We know that if we're parallel or anti-parallel, as in theta is 0, then the force is 0. And if we're 90 degrees or perpendicular, we've got a maximum force. So we would expect some relationship in the middle. It shouldn't just be off-on sort of scenario. If we take a conductor of a length L and it's carrying a current I in a uniform magnetic field B at some angle theta, then the force on this wire is given by this formula. So it's very similar to what we saw before. We've got our IL, we've got our magnetic field, but now we're considering an angle. So this is the force on the wire, which is our current carrying conductor here. We've got the current that's flowing through the wire. We've got the length of the wire, the strength of the magnetic field, and the angle between it. This comes from the thing we saw earlier, the B equals FIL. We've just rearranged to get the BIL part, and we've got the F, but in this case, this was factoring in a sine theta of 1. So for any situation, we keep the sine theta, and now we can just plug in a value if we know an angle. So in summary so far on the magnetic interactions, the magnetic force on a current carrying conductor placed in a magnetic field is at a maximum when the current is perpendicular to the field, and it's equal to F equals ILB, because that sine theta has become 1. It's 0 when the magnetic field is parallel to the current, because F equals 0 as the sine theta equals 0. And at any intermediate value when the current is at some angle to the field, it's given by F equals ILB sine theta. As long as you remember this formula, it's easy to figure out what else is happening, because you can work out that sine theta is 0 and sine theta is 1 at 90 degrees and 0 degrees. Magnetic conventions act in the same way that the electric field conventions did. When we see this cross, it is just like the back of an arrow going into the page, so we say the current is traveling into the page. When it comes out, we say we see the dot, and this is the current coming out of the page. For a magnetic field, we use exactly the same thing, but we don't draw the circles. So you still see crosses and dots, but we don't have this circle. You can think of this circle as like the thickness of the wire or something like that, and this is the arrow or the arrow wire going into the page, the arrow wire coming out of the page. So that's your current, and plain dots and crosses are magnetic fields. Let's have a go at this one. So in this case, we're using that notation. State the direction and the magnetic force on each of the conductors below. So this would be using your right-hand rule.
expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids. Math, science, history, unraveling the mystery that all started with a big bang. Bazinga.
Okay, so looking at this, the first one, the force on the conductor is directed out of the page. We use that right hand finger rule, we get the current magnetic field, and the third finger is pointing towards us, so out of the page. In the next one, directed to the right, and the third one directed up the plane of the page. In this case now, we're talking about calculating the magnitude of the magnetic force acting on a 1.5 centimeter length of conductor. If we've got magnetic field strength, we're given the current that's flowing through it. Then we, in part B, they're asked to state the direction, and then 3 uses that angle rule. So we're using we've got the magnetic field, we know the length, we know the current, and we're trying to calculate the angle. So if we know what the magnetic force is, reverse engineer that formula and figure out what the actual angle is of that thing there.
Link, here come to town, come to save the Princess Zelda. Got it poker away, now the children don't play, but they will when Link saves the day. Hallelujah! Now Link, fill up your hearts so you can shoot your sword with power. And when you're feeling all down, the valley will come all out, so you'll be brave and not this is a coward. Now Link has saved the day, but got it in his granite. So now our Zelda is free, and now a hero shall be. Link, I think your name shall go down into history.
So here it is. Using the ILB sine theta rule, we find that 20.26 newtons is the force on this object. Direction, right hand rule tells us that it's perpendicular out of the page. And in question 3, we reverse engineer the formula, we rearrange for theta, plug our values in, and we get 44.2 degrees is the angle of that current carrying conductor. From here, have a look in the workbook. Page 194, question 1 to 8 cover concepts that we've looked at in terms of forces on current carrying conductors, things like that. Have a look at those questions, and I'll see you next lesson.